Hello, everyone, and here's the video I promised you that was to supplement the part of the 2.4, 2.5 lecture that I emailed about a little bit earlier. For the purposes of this lesson, let R represent the rank of the coefficient matrix of a system of equations. Let R pounds represent the rank of an augmented matrix. Now, those are both whole numbers, and traditionally with whole numbers, there's three options. One is the numbers can be equal to another. One is one of the numbers can be greater than the other, or vice versa. Now, for the purposes of this lecture and what these numbers represent, it does not make sense for the coefficient matrix to have a larger rank than the augmented matrix because the coefficient matrix is the same as the augmented matrix minus a column. And that additional column gives it an opportunity to have an extra pivot, and so therefore the augmented matrix will at least have the same number of pivots or more than the coefficient matrix. All right, so now that that's out of the way, we're only looking at cases 2 and 3. Let's look at a simple 2 by 2 system, okay, that we can all eyeball the answer to. Let's say we have a sum of two numbers, that's 10, and the difference of the same two numbers is 4. Now we can all see that 7 and 3 are the solution to that system. Now showing it via matrices is pretty simple. Okay, you have an augmented matrix that looks like 1, 1, 1, negative 1, dot, 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 10, 4. And we can do some elementary row operations. Okay, so let's let R2, or the new R2, be R1 minus R2. 1 minus 1 is 0, 1 minus the negative 1 is 2, 10 minus 4 is 6. Row 1 was unchanged, 1, 1, 10. Okay, next up, let's say R2 prime is 1/2 of R2, so we scale this down. So we get 0, 1, and 3, because we want a pivot in the bottom row. So that's 1, 1, and 10. Okay, so we have, two pivots now? One there and one there, so this is row echelon form. We can place this in reduced row echelon form by saying R1 prime is R1 minus R2. So 1 minus 0 is 1, 1 minus 1 is 0, 10 minus 3 is 7, and we get 0, 1, 3, dot, dot, and this is reduced row echelon form. Remember, everything below a pivot has to have a 0, and everything above a pivot has to have a 0 for it to be in reduced row echelon form. Okay, and so you can easily see here, this system of equations, maybe I can fit it in right here. 1x1 plus 0x2 equals 7, hence x1 equals 7. 0x1 plus 1x2 equals 3. And so your solutions are 7 and 3. Now, we fell under this category where if we looked at the coefficient matrix, we had, so let me draw a line right here. So let's write the coefficient matrix. And let's write the augmented matrix. The coefficient matrix for this example was in reduced row echelon form 1, 0, 0, 1. The augmented matrix was 1, 0, 7, 0, 1, 3. So you can see that the two pivots that were in the coefficient matrix are present in the augmented matrix. Okay, so we fall under condition number 3, where R equals R pounds. So under that circumstance, we can see that you do have the potential of having a unique solution. Okay, let's look at a pair of different coefficient and augmented matrices. Okay, what if we had a coefficient matrix of let's see, let's find one where the coefficient matrix has one fewer pivot. So 1, 0, 0, 0. And the augmented matrix was 1, 0, 7, 0, 0, 1. Okay, so here's one pivot in the coefficient matrix. Here are two pivots in the augmented matrix. Okay, so now we're under circumstance number 2. What does the corresponding system of equations to this one look like? Well, it looks like 1x1 plus 0x2 is equal to 7, and 0x1 plus 0x2 is equal to 1. Okay? And this doesn't have to be a 1 right here. It can be a 1, a 2, a 3, a 10 million, okay? Because we can rescale this row, divide by 10 million, and always retrieve 0, 0, 1 out of this. Now think to yourself, what pair of numbers, when multiplied by 0 and then added together, equal 1? The answer is none. So, when we're in this circumstance where R is less than R pounds, you're going to have an inconsistent system. Whenever the final pivot is in the augmented column, you will have an inconsistent system of equations. So we've taken care of the case where there's unique solution. We've taken care of the case when there is no solution. There's one last case that we have to think about, and that's when there's an infinite number of solutions. What does that look like? 1, 0, 0. Well, we know this can't be a 1 right here, because if this is a 1, you're going to be in case number 1, and then you're going to have a unique solution. So that makes this a 0. We know that this has to be 1, 0, 0, 0. Okay? The only way for this to differ from the previous two examples is if there wasn't a pivot at all in the augmented column. So let's make this a 0. So what does this system look like? I'll write that in, well, I'll write it in red. We have 1x1 plus 0x2 is 7. That's fine. Then you have 0x1 plus 0x2 is equal to 0. Now, can you think of pairs of numbers that make that system of equations true? I can think of a whole bunch. Okay, I can think of any pair where the first component is 7 and the second component is arbitrary. Call it t. Okay, x2 can be anything it pleases. As long as x1 is 7, the system of equations in red is true. So here, and notice that the number of pivots in the coefficient matrix and the number of pivots in the augmented matrix are the same. So we're back under condition number 3. So we have a different branch here. You either have a unique solution or you have an infinite number of solutions. Okay, now this is not an official proof, but this is true, and we don't need to prove it hopefully for you guys to believe it. So, using this information, okay, let's look at a slightly more complicated example. 2x1 minus x2 plus 3x3 minus x4 is 3. 3x1 plus 2x2 plus x3 minus 5x4 is negative 6, and x1 minus 2x2 plus 3x3 plus x4 is 6. So the augmented matrix is shown to be row equivalent to this matrix. And I'm not going to do this this is work that needs to be shown. But I don't want to bore you to tears with this because we're beyond section 2.4, and so now we need to look at some of the consequences of 2.4. Here, let me write down the coefficient matrix. The coefficient matrix is, for the reduced row echelon form, this is actually it's row echelon form. Sorry about that. Let's make this into reduced row echelon form. How should we do that? Let's see, here are my pivots, 1 and 1. There's a 0 below, but not above. So let's multiply the second row by 2. So our new R1 prime, is going to be our old R1 plus 2 times R2. So row 3 remains 1, 2, 3, 4, 5 zeros. Row 2 remains 0, 1, -1, -1, and 3. Row 1 is what? So it's row 1 plus twice row 2. So 1 plus twice 0. -2 plus twice 2. 3 plus -2. That's 1. 1 plus 2 times -1. So that's 1 minus 2. That's -1. And what's this? 6 plus 6. That's 12. Dot, 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 dot. Now, we are in reduced row echelon form, our REF. Okay. Now, once we're in reduced row echelon form, let's write the coefficient matrix. The coefficient matrix is 1, 0, 1, -1, 12, and 0, 1, -1, -1, 3, and zeros. Oops, sorry, that's not the coefficient, that's the augmented matrix. Let's get rid of that. There's the coefficient matrix. Here's the augmented matrix for the reduced row echelon form. Let's underline our pivots. Okay, there's a pivot there, there's a pivot there, there's a pivot there, there's a pivot there, there's no pivots down there. Okay, so we're under the circumstance where the augmented matrix and the coefficient matrix have the same number of pivots. Now, is there a unique solution or is there an infinite number of solutions? To answer that question, okay, what we can do is, well, we can do a number of different things. First off, kind of compare these to the 2x2 examples, okay? Here, there was a unique solution when there was a pivot in every row. Here, there was an infinite number of solutions. There wasn't a pivot in every row, and we had a row full of zeros at the bottom. So, just by comparing one example to another, it appears as though that the solution to the new system is going to have an infinite number of solutions because there's not a pivot in every row. And there's a string of zeros here at the bottom. Let's see if we can verify that. Looking at the reduced row echelon form, that augmented matrix can correspond to the system x1 plus 0x2 plus 1x3 minus 1x4 is equal to 12. 0x1 plus 1x2 minus 1x3 minus 1x4 is 3. And we have a bunch of zeros. 0 plus 0 plus 0 plus 0 is 0. There is no equation for x3. Okay, the best that we can say is x3 is equal to itself, and x4 is equal to itself. Okay, now the book doesn't adopt that notation. Okay, generally it'll call this something like t and call this something like s, where s and t are real numbers. And this is indicating that x3 is a free variable. It can be anything it pleases. x4 can be a free variable. It can be anything it pleases. And once x3 and x4 are declared, then we know what x1 is. x1 is going to be equal to 12 minus s plus t. How do I get that? Take this equation and solve for x1. So subtract x3 over to the other side, add x4 to the other side. x3 is s, x4 is t. You get x1 is 12 minus s plus t. x2 is going to be equal to 3 plus s plus t. Okay, again, you're adding x3 and x4 to both sides. x3 is s, x4 is t. x3 is s, x4 is t. And so the solution to the system will look like the set of ordered points that look like 12 minus s plus t in the first component, 3 plus s plus t in the second component, s in the third component, t in the fourth component. And that's what the solution set to the system of equations is. Okay, so I hope this gives you all the information that you'll need. I'm sorry that examples like this weren't included in that 7th video, or the lectures number 7 video. So I'll add that to YouTube right away.